Hi, in the last section of this chapter we talk about the subsequences. So if I take for example the sequence U1, U2, U3, U4, U5, etc., U6, U7, U8, U9, U10, and etc. So for example U1 can be equal to 1, U2 to 2, 4, 10, 5, minus 1, 11, 13, 14, minus 1, etc. So I will define a new subsequence, which will be a sequence extracted from UN. But to extract the sequence, I will follow some rules. First, I will select terms with an increasing pattern. So I cannot select, for example, U1, U4, then U2. No, I need to be increasing all the time. When I say increasing, I'm talking about the index of the sequence that should be increasing, not the numbers in here. So I will take, for example, let's say I will take U1, then U3, then U4, then U5, then U7, then U9, etc. So I'm taking according to a pattern. I'm selecting all the terms with odd indices. Okay, so UN will be U1 will be V0, U3 will be V1, U5 it's V2, U7 is V3, and U9 is V4. Okay, so I'm defining a new sequence. V0 of course is equal to 1, V1 is equal to 4, it's equal V2 5, V3 is 11, and V4 is 14. So V0 is equal to U1, V1 is equal to U3, V2 is equal to U5, V3 is equal to U7, and V4 is equal to U9. So I selected terms with a definite clear pattern, which is the odd numbers. And the second condition for the sequence to be a subsequence of the sequence UN is that the selection will not stop. I'm not choosing a finite number of terms, I'm choosing a terms according to a pattern, and these terms will continue. So I'm taking U11, U13, and etc. So this way I defined a sequence Vn that is a subsequence, or that is extracted from the sequence UN. So to write it more mathematically, I will define a mapping sigma that goes from n to n. So it's a function that goes from n to n, and that corresponds to each n. For example, in this case, the number 2n plus 1. It means that for the index 0 of V0, the image will be 1, so it will be 1. So if you want to know what is V0, all you need to do is to calculate 2n plus 1, which will be 1, so V0 will be equal to U1. And then V1 will be equal to U3, because sigma of 1 is equal to 3. And V2 will be equal to U5, because sigma of 2 is equal to 5. And sigma of 3 is equal to 7, and sigma of 4 is equal to 9. So defining this mapping, you will define how you are selecting the terms. Okay, so this mapping should be, of course, increasing, because having this mapping increasing will ensure that your choice will be an increasing choice. So you are not choosing U1, U5, then U2, then U9, then U6, which is not allowed in the selection to construct a subsequence. Okay, so back to the course here. Let sigma be a strictly increasing mapping, strictly increasing, so we are not choosing a term twice. Let Un be a sequence. A subsequence of Un is defined as the sequence U sigma n, so what I called U sigma V sigma n in my example, so it's U sigma n. In other words, a subsequence is an infinite selection of elements of the original sequence with increasing indices. Let's check some examples. Choosing, for example, the first sigma, or one of the sigmas, as being 2n, we are choosing all the elements with even indices. Choosing sigma as being 2n plus 1, we are choosing all the elements with odd indices. So for this sigma, the subsequence will be U0, U2, U4, U6, etc. And for this sigma, it will be U1, U3, U5, etc. Okay? Now, we can prove that choosing sigma as being a mapping from n into n and being strictly increasing means that sigma n is greater than n. So you cannot have, for example, sigma of 3 less than 3. It would be, of course, greater than 3. Of course, you can prove this by induction, because if you have the proposition true for n equal p, then of course you have sigma of p greater than p, then of course sigma of p plus 1 will be greater than sigma p, because the mapping is strictly increasing, which is greater or equal to p. So of course sigma of p plus 1 will be greater or equal to p plus 1, because sigma of p plus 1 is an integer which is greater strictly than p, so it can be p plus 1 or greater. So this proposition, we will use it to say that if a sequence converges to L, then any subsequence of un converges also to L. We need to use the proposition of sigma in this proof in here. So we are saying that if we have a sequence, a convergent sequence, then any subsequence you choose will be also convergent and to the same limit. It's not difficult to prove, because if un is convergent to a limit, then un minus L will be less than epsilon according to the definition, right? So if you have epsilon positive, there exists a rank such that all the elements above this rank will satisfy un minus L less than epsilon. So defining any subsequence, we will have a sigma that is strictly increasing. So we have a sigma satisfying the proposition that we did in here, sigma of n greater than n. So since we have un minus L less than epsilon for any n greater than n, then for sure you will have sigma of n greater than sigma of n, right? And sigma of n according to the latter proposition is greater than n. Then sigma of small n is greater than big N, which means that the elements u sigma n will satisfy un minus L less than epsilon, because they are elements with indices greater than big N. So we will have u sigma n minus L less than epsilon, which means that u sigma n is convergent to L according to the definition of the limit. Now, of course, if you have a subsequence that is converging to a limit, it doesn't mean that the sequence is converging to a limit. For example, if you take the sequence minus 1 to the power n, it's a non-converging sequence. But if you take the sequence of odd indices, it's a constant sequence equals to minus 1, which is converging to minus 1. And if you take the subsequence with even indices, it's a constant sequence equal to 1, so it's converging to 1. So both subsequences with odd and with even indices are converging, but the original sequence is not converging. So if you have many converging subsequences, it doesn't mean for sure that the sequence is converging. Okay? Especially in this case, you have subsequences converging to different limits. And to finish, we will state the Bolzano-Weierstrass theorem that says that every bounded sequence in R has a convergent subsequence. So if the original sequence is not converging, maybe. If it's convergent, then any subsequence will be converging to the same limit. But if it's not convergent, if it's only bounded, like this one, okay, this one is bounded, then you can find at least one convergent subsequence of the sequence. So if it's bounded, you can find at least one converging subsequence. I will prove an example to finish the chapter that will state that if you have some subsequences converging to a limit, then the original sequence will be converging to the limit in some conditions. So if the selection of the subsequences is special. So in here, for example, we are taking u to n, which is the sequence with even indices, u to n plus 1, which is the subsequence with odd indices, and then un squared, which is the sequence with squared indices. So if these three sequences are convergent, or these three subsequences, then the sequence un is convergent. And I will recall, this is not true for any selection of subsequences. Here we have a very specific selection with which is the subsequence with odd indices, with even indices, and with the square indices. Of course, they are good definitions of subsequences, because 2n, so sigma of n equal to n, is a strictly increasing mapping from n to n plus 1 as well, and n squared as well. So again, having un a sequence and having the three subsequences u to n plus 1, and un squared, we need to prove that if u to n plus 1, and un squared are converging, then un is convergent. So in the given of this example, we are not saying that u to n plus 1, un squared are converging to the same limit. So we need to assume that they might be converging to different limits. Okay, of course, if they are converging to different limits, then the sequence un will not be convergent. So we need to prove that they are converging to the same limit, and the same limit, this limit is the limit of un, which will be converging. In fact, if we said that, we said two things. First, if un is convergent, then it has any subsequent is also convergent to the same limit. We said also that if you have a subsequence converging to a limit, doesn't mean that the sequence is convergent. And we said that if a sequence is bounded, then it has at least one converging subsequence. Now I will say something more, that if you have u to n and u to n plus 1 convergent to the same limit, then of course un will be convergent and to the same limit, because u to n and u to n plus 1 together, they form all the terms of the sequence. So if they are convergent to the same limit, then all the terms are converging to the same limit, then un will be convergent to the same limit. So what we need to prove in here is that first, u to n plus 1, un squared are converging to the same limit, otherwise un will not be converging. Then, once we have them converging to the same limit, we will deduce from the fact that u to n and u to n plus 1 together are converging to the same limit, we will deduce that un is converging to the same limit. Okay? So let me a little bit explicit these sequences. So u to n is the sequence given by u0, u2, u4, u6, u8, u10, u12, u14, u16, u18, etc. This is u to n. u to n, un squared, I will write in here, is given by u0 for 0 squared, and then u1 for 1 squared, and then u4 for 2 squared, u9 for 3 squared, u16 for 4 squared, u25 for 5 squared, u36 for 6 squared, u49 for 7 squared, and u64 for 8 squared, etc. And u to n plus 1 will be given by u1, u3 for 2 times 1 plus 1, okay? So u5, u7, u9, u11, u13, u15, u17, u19, etc. So we know that any convergent sequence, or if you have a convergent sequence, any subsequence will be converging to the same limit. So if you take the first one in here as being a convergent sequence, which is the case, then any subsequence will converge to the same limit. And if you take this sequence in here and you take a subsequence from it, it will be converging as well to L3 because un squared is converging to L3. So if we are able to take a subsequence from u to n and another subsequence from un squared such that these two subsequences will be the same, it means that the first subsequence will be converging to L1, the second one, which is the same as the first one, which will be converging to L3, and since the limit is unique, then L1 will be equal to L3. I will re-explain. If you take the subsequence, the following subsequence: U0, U4, U16, U36, which should be somewhere in here, right? And you continue. So you took a subsequence from u to n, which is the same a subsequence of un squared, and since u to n is convergent, then this subsequence is convergent to L1, and then since un squared is convergent, then this same subsequence is convergent to L3, but the limit is unique, so L1 should be equal to L3. Okay, so we need to find a subsequence that is common to u to n and un squared. So choose or find first a subsequence common to u to n and un squared. Okay, so we choose u4n squared, which will represent u0, u4, u16, u36, etc. If you take this sequence, it's by intuition. You should look to the sequence and try to find this relation. So sigma of n being equal to 4n squared is a strictly increasing mapping from n to n. So it's a good subsequence. So choosing this subsequence, u4n squared n is a subsequence of u to n, then it is convergent or converging to L1. u4n squared n is a subsequence of un squared, then it is converging to L3. But since the limit is unique, then L1 is equal to L3. Okay, now again, let's do the same between un squared and u to n plus 1. We have to find something in common. So if we take, for example, u1 with u1, u9 with u9, u25 with u25, which is somewhere in here. Okay, what's the relation that defines this sequence 1, 9, 25, etc.? So also choose u, it's u to n plus 1 squared. So choosing this relation u to n plus 1 squared, let's see, for n equal 0 it's equal to 1 squared, so 1. For n equal 1 it's equal to 2 plus 1, which is 3 squared, 9, so it's 9 now. If for n equal 2 it's equal to 5 squared, so it's u25, etc. This is the good relation. So choose this one, u to n plus 1 squared is a subsequence of u to n plus 1, then it converges to L2. Also, u to n plus 1 squared is a subsequence of u n squared, then it converges to L3, but the limit is unique, then L2 equal L3. Therefore, we have L1 equal L2 equal L3. So, finally, u to n converges to L equal L1, u to n plus 1 converges to the same L, which is equal to L2. Okay, so this is the same limit, and u to n and u to n plus 1 covers all the terms of un, then un is convergent and limit of un is equal to the same L when n tends to plus infinity. And this is what ends chapter 2.